Hello everyone, I'm Srikant from Mobile Computing Laboratory in Osaka University. Today, I'll be presenting our paper titled Optimizing Unlicensed Coexistence Network Performance Through Data Learning. So let's begin. The growing adoption of technologies such as mobile augmented reality, or in short, AR, is going to push the data demand to 300 exabytes by next year. The AR market is expected to grow over tenfolds in the next few years, but these projections rely heavily upon cellular networks. For a truly seamless and mobile AR experience, low latency and high capacity cellular networks are extremely vital. To meet these requirements, cellular service providers have adopted new paradigms such as the LTE Wi-Fi coexistence networks and also resorted to a consistent densification of networks. However, the advancements in coexistence networks and network densification have presented new challenges, and our paper aims to address some of these problems. Before we begin this discussion, please note these important terms as they will be used frequently throughout this presentation. So, the first question is, why do we need LTE Wi-Fi coexistence for AR? Well, there's enough research to conclude that LTE is not sufficient to offer the low latency and high capacity that AR applications and services require. While 5G will be a game changer for the proliferation of AR, LTE and LTE Advanced will be the dominant cellular standards for the next few years. This is where LTE Wi-Fi coexistence shines. It harnesses the unlicensed spectrum to offer enhanced quality of services to the end user. As a result, there has been a rapid deployment of unlicensed LTE Wi-Fi coexistence networks. But proliferation of new network technologies presents new challenges, as we'll see ahead. The first problem is the analysis of unlicensed coexistence networks. Two competing unlicensed LTE standards have been put forward, which are LTE-U and LTE-LAA, and a lot of debate and research has been devoted to comparing these standards. However, most of the existing studies are limited to comparing network performance evaluation metrics such as throughput, latency, etc. in these two standards. This work enhances the existing comparative analysis of LTE-U and LAA by conducting feature relationship analysis of network data. The network feature relationships, or NFRs, learned from network data have an additional utility. There has been a consistent densification of cellular networks through a concentrated deployment of low-power small cells. End-to-end multi-user AR latency is already high in public LTE networks, and there is a valid concern that consistent densification may impact the performance of AR applications even more adversely. This makes optimization in dense coexistence networks, time critical, and we believe that network feature relationships can play a crucial role in accelerating dense network optimization. That is the most innovative aspect of the ideas presented in this work. From a high-level perspective, our project can be broken down into three components. First is conducting feature relationship analysis of experimental and public LTE Wi-Fi coexistence networks. The second step entails leveraging the learned NFRs in optimizing dense coexistence networks. And finally, in the ongoing research, we are devising ways to apply these solutions to AR applications and services. So now, let's go over the specific contributions of this work. We performed feature relationship analysis of dense coexistence networks which were implemented on experimental test beds. A comparative study of LTE-U and LTE-LAA was done, which explored new dimensions such as strength of feature relationships, precision and stability of relationship models, and more. Impact of factors such as bandwidth allocation and the choice of predictor variable is also analyzed. We then tried to solve the time-critical optimization problem of dense networks by utilizing the learned feature relationships. The solution seems quite effective, as we were able to reduce convergence time while maintaining high accuracy. So let's look at these contributions in detail, beginning with the experimental setup. The National Instruments Rio testing platform, along with the LabVIEW system, served as the LAA and LTU testbed. The system offers high operational flexibility through advanced user-defined configuration parameters such as subcarrier modulation scheme, LAA transmission opportunity, etc. Netgear wireless routers are used to design the Wi-Fi testbed. They support 802.11n and AC in the 5 GHz band. More technical details on the testbed are presented in the parameters table. Several experiments were designed to explore dense unlicensed coexistence performance by creating combinations of LAA and LTEU, 802.11n and 802.11ac, and varying bandwidths from 5 to 20 MHz. Dense random topologies were considered where nodes were placed at an internodal distance of 5 to 10 meters. Experiments focused on gathering SINR and throughput data for NFR analysis. All experiments were carried out in an indoor setting at the University of Chicago campus. Now let's look at the analysis methodology. Let's begin with the learning algorithms used in this work. Regression is a popular machine learning paradigm used to determine the relationship between network parameters in continuous space. Linear and kernel-rich family of regression algorithms were used to learn SINR and capacity relationship. Local outlier factor algorithm was used for outlier detection and removal. Models were selected based on each model's R-square or regression model validity determined through k-fold cross-validation. The LTEU and LAA models were compared in two ways. First was the scenario-specific comparison, which comprised of 32 test scenarios based on unlicensed LTE variant, Wi-Fi variant, the bandwidth considered, etc. Second comparison was aimed at larger component-level trends, such as the performance of SINR as a predictor as compared to capacity as a predictor. While the network performance metrics were measured and considered in the comparative study, the focus was primarily on learning model parameters. These include regression model validity or RMV, residual error or RSD, outlier percentage, and the gain in the model validities after outlier removal. The findings of our dense coexistence network data analysis are presented next. Let us begin with a comparison of LTEU and LAA on modeled strengths. As far as RMV is concerned, LTEU and LAA show comparable results. This, however, does not imply that the feature relationship models for both are equally reliable. This is because model validity is not the only metric for goodness of fit. Let's look at other metrics ahead. Residual error, or RSD, is a measure of precision of a model's predictions. In terms of RSD, LAA significantly outperforms LTEU in both scenario-specific and configuration-level comparisons. This is regardless of factors such as bandwidth or the choice of predictor variable. Therefore, LAA models seem to be more precise and accurate. Likewise, in terms of other feature relationship parameters such as the deviation in model validities or the percentage of outlier in the data, LAA models fare much better than LTEU models. This implies greater stability and fewer fluctuations in network feature points in LAA. A similar comparison of the coexisting Wi-Fi standards reveals a somewhat different trend. While 802.11ac demonstrates a much higher average throughput than 802.11n, in terms of feature relationship parameters, AC appears to only have a slight edge over 802.11n. This begs the question, why is there only a marginal difference between the Wi-Fi standards? Upon further analysis, we find that within the LTE Wi-Fi coexistence system, the unlicensed LTE component is the primary determinant of the overall system performance. An adverse impact of the unlicensed LTE on Wi-Fi is visible, and it is more prominent in the case of LTEU. This can be attributed to the duty cycle-based channel access mechanism of LTEU. So, two important inferences can be drawn from a feature relationship perspective. One, LAA coexists better with Wi-Fi than LTEU does. And second, the overall system performance in the coexistence environment is dominated by the unlicensed LTE component. We also see a very visible and strong impact of the choice of predictor on network models. We observed that the capacity is a reliable predictor of SINR, but the reverse may not necessarily be true. This shows the bidirectional nature of feature relationships and also hints at the possibility of additional feature points that may improve the network models. Coming to bandwidth. On the surface, it appears that with increasing bandwidth, there is a greater fluctuation in unlicensed coexistence network performance. This would be worrisome for QoS guarantees. However, analysis of normalized data confirms that there is no increase in residual error with bandwidth, which is very promising. These were the major findings of the analysis. Next, I will present an innovative solution to dense network optimization by utilizing network feature relationships. The proposed solution is named Network Feature Relationship Based Optimization, in short, NEFRO. It entails gathering network data in real time or in predefined time epochs, learning feature relationships from the gathered data, and using them as constraints in the optimization formulation. NEFRO has certain benefits over conventional optimization approaches. By using NFRs, it accounts for the ambient network environment. It lowers convergence time and maintains high accuracy vis-a-vis the baseline models. These features make NEFRO ideal for time-critical dense network optimization. Let's review the validation of NEFRO and our hypotheses. For validation of NEFRO, four recent network optimization models from the literature are used as the baseline models. Two of them seek to optimize network capacity, while the other two optimize signal strength. They are implemented on the GAMS tool for the test scenarios described earlier in the experiment design. The baseline optimal values for network capacity and signal strength are observed. Next, for each of these models, the NEFRO optimal values are determined by using the learned capacity interference relationship as a constraint instead of the corresponding theoretical constraint. Finally, the baseline and NEFRO optimal values are compared on two parameters. First is accuracy, which indicates the closeness of NEFRO optimal value with the baseline value. And second is the convergence time fraction, which is a measure of reduction in convergence time. High accuracy and low convergence time is highly desirable. With this evaluation framework in mind, let's look at the results. For capacity optimization, NEFRO performs remarkably well by reducing the required convergence times while delivering NEFRO optimal values very close to the optimal results of the respective baseline models. In LAA scenarios, NEFRO offers a significant reduction in convergence time, while in LTE scenarios, the CTF is somewhat subdued. The NEFRO approach seems to work better for LAA scenarios. It still outperforms baseline capacity optimization models for both LAA and LTEU. Coming to signal strength optimization. For LAA scenarios, NEFRO performance for SINR optimization is as good as it was for capacity optimization. However, in LTEU, there appears to be a difference in NEFRO performance for these two objectives. Although there is a favorable convergence time and accuracy trade-off for LTEU, on average, the magnitude of the gain is less than 5%. This is because network optimization in LTEU is inherently more challenging due to its channel access mechanism. Hence, it is more computationally intensive and requires a longer convergence time. Overall, the average performance of NEFRO across all test scenarios for the four optimization models is impressive, which validates NEFRO and the proposed hypothesis. This brings us to the end of the discussion on the ideas presented in our paper. Now, let's look at some major takeaways and the future direction of our research. First and foremost, it can be stated with great confidence that feature relationship analysis is a useful tool for network performance evaluation. It offers insights on the interactions of various network parameters or feature points. Further, the major inferences that can be drawn from the analysis presented in this work are as follows. LTLAA fares better than LTEU in terms of predictive accuracy and stability of the capacity interference models. Second, within the coexistence system, unlicensed LTE is the dominant component that seems to determine the overall system performance. Unlicensed LTE also has an adverse impact on Wi-Fi, but LAA appears to coexist better with Wi-Fi than LTU does. Choice of predictor variable is a crucial aspect when performing network feature analysis. Next, fluctuation in network performance in the unlicensed spectrum does not seem to rise with increase in bandwidth, which is highly desirable for great end-user experience. Moving on to dense network optimization. Network feature relationships can help accelerate the optimization process for time-critical applications and services such as augmented reality. This hypothesis is validated through the proposed Network Feature Relationship-Based Optimization, or NEFRO framework, which maintains high accuracy while reducing convergence times vis-a-vis baseline optimization models. NEFRO is versatile and can be used for multiple network optimization goals, such as throughput or signal strength. In terms of overall convergence accuracy trade-off, NEFRO fares better than the baseline models for both LAA and LTE-U dense coexistence scenarios. However, it seems to work better for LAA than it does for LTE-U. We are currently devising methods to apply these solutions to a simulated AR application. We are also analyzing the accuracy and convergence time trade-off in dense network optimization when higher-order feature relationships are involved. With this, I would like to conclude my presentation. Thank you so much for your time and attention. Please feel free to reach out to us through email or our lab's website listed below. If you have any questions, I'll take them now. Thank you very much.